In today's video lesson, we'll talk about ways of using the Pythagorean theorem for somewhat practical situations. In class, I'll be talking about a box of roses, and what the longest possible rows that would fit through that would be. That's going to use this concept of the 3D diagonal that you can see here. Another one is sometimes the length of one side of a right triangle compared to another side is some relationship that's known to be some ratio, like in my square right here. Well, it's not a square, it's just half of a square, but those two sides, both being x, indicate that they're congruent. And we can use the Pythagorean theorem then to find the unknown side, even though there are two of them that are unknown. In the 2D diagonal, we can just use the Pythagorean theorem, noting that one side is A, another side is B, and this dotted diagonal would then be C. That's pretty straightforward and standard, just like I talked about in the previous video lesson. But what if the diagonal goes from one corner of a three-dimensional box to the opposite corner, like you see here? If I do a cross-section through the box, it will end up turning it into two ramps, one that's upright, one that's upside down, kind of like these blue dotted lines indicate. The dashed line through the box is still the diagonal from one corner to the opposite corner, but that would be basically the diagonal across the 2D plane, which is the top surface of the ramp. This is all very difficult to imagine, and you have to get used to looking at three-dimensional pictures on two-dimensional screens and paper. But if I'm talking about the bottom ramp now and the top surface of it, that dashed line, not the dotted line, but the dashed line is what I'm looking for. The dotted line, which shows basically the slope of the ramp, can be found using the Pythagorean theorem, just as with the two-dimensional drawing. So A could be something like this side, B could be something like that side, and C could be my blue dotted line, not dashed line, but the blue dotted line that would indicate the slope of the ramp. Once I have found C, I can then use that in the second part of the problem where I'm trying to find the dashed line. So C would then become either A or B in the new triangle, which is indicated by this green triangle I'm about to draw. So this green triangle, C, is now a known length. And hopefully this other side over here would be as well, x. And so finally the hypotenuse of that, the original dashed line, I would be able to find that. And I'll show you an example of that in class today, but this just should serve as a reminder of what the procedure is. Here's another example of that. This three-dimensional box, I know all of the side lengths. Those would be measurable using like a ruler or something like that. The blue hypotenuse is just along the bottom surface of this box. It is unknown. I'll use blue as I solve for that. I need 6 and 10 as my lengths that are along the bottom surface. So 6 squared plus 10 squared is equal to, I'll call it C squared. So I'm going to get 36 plus 100 equals C squared. And then when I do my addition here, I get 136 equals C squared. That was a bad C. And then I square root both sides. And C is equal to the square root of 136. And for the purposes of our class, we're just going to leave it like that. It probably can be simplified, or given a decimal approximation. But what we're about to do in just a second is to use that number and then square it again. So I'm just going to get my 136 back. So I just discovered that the blue line is, well, I called it C, and that was the square root of 136. I'm going to use that value now to find the the length of the red line, the diagonal through the box. So what was C, or my answer for the blue line, becomes, maybe we'll call it A for the next problem. So square root 136 needs to be squared plus my vertical distance here, which is indicated by this green line, that's going to be 15, which is the side length of the box. That also is squared. And that is equal to the new c squared, which is the red line. So it's my new hypotenuse. Okay, so 136, or square root of 136 squared becomes 136. 15 squared is 225. 136 and 225 add to 361. And then we square root both sides. Holy cow. Square root of 361 is a whole number. 19. So the diagonal distance through that box would be a whole number, 19 centimeters. And that's how you do it. It's a two-step. You've got to do find a diagonal across one of the faces, which was my blue line, and then you can find a diagonal through the box, which was my red line. Okay, suppose I had a square where the side lengths weren't known, but the diagonal across it was. And I've completed this square using my blue lines here, but the problem didn't have this originally. All of the sides of the square would be length x. That's the same length and it's unknown. But the diagonal is known, and so I can use the Pythagorean Theorem. Since it's a square, the corners would form right angles, and so the parts that are in black here must form a right triangle. I can use the Pythagorean Theorem then to solve this. So a squared plus b squared equals c squared. Substituting values that I have from the problem, I would get x squared plus x squared equals let's see, 3 square root of 2 quantity squared. Left side combines to 2x squared. And the right side, when I do the multiplication on this, I'm going to, let's just expand this using what squared really means. Squared means that number times itself. So I've got 3 square root 3, or square root 2 times 3 square root 2. If I use the commutative property of multiplication, I can get 3 times 3 times square root 2 times square root 2. I have just rearranged the parts that I'm multiplying together. There are 4 of them, 2 of them being 3's, 2 of them being square root 2's. When I do the simplification on this, I'm going to get 9 for the 3's, and square root 2 times square root 2 is the same thing as square root 2 squared, which is just 2. So the right side of the equation actually becomes an 18. Then when I divide both sides by 2, that reduces. I get x squared equals 9, and so x must be 3. Here are the problems that I would like for you to try. These are just like the ones that I did in this video lesson, so if you need to, go back and review the examples. But these will be transferred to our warm-ups tomorrow in class. Good luck!